In this video, we are looking at signals and its characteristics. This is the second part of our video on data representation and signals. So what is a signal? A signal is an electric or electromagnetic or even a light impulse that is used to encode and transmit or carry data. That is the definition of a signal. And then others also define a signal as a time-varying waveform. It's a waveform that is used to carry data. So all these two definitions have something in common, that signals carry data. The words we see there, the new or keywords we see there are encode and probably maybe transmit and electromagnetic. We know what electric is. An electromagnetic signal is any signal that has a magnetic and electrical component. So that is just it. And encoding, we say that the signal encodes the data. What we mean is that the signal transforms the data to something that it can carry. That is all. So bear in mind, outside of the technical terms, bear in mind that signals carry data. If you are transferring data from one device to the other, the data by itself cannot move from one device to the other. It has to be carried on something called signals. So signals just carry data, and they are waveforms that the data is put on and then transferred from one device to the other. There are mainly two types of signals: the analog signal and then the digital signals. So we will quickly look at what they are. So we say that analog signals are represented as continuous waveforms that can be at infinite number of points between some given minimum and maximum. Let's go to the next slide and I'll show you what a waveform looks like. So these three here are examples of a waveform. That's a signal, but these waveforms are analog signals. So these are the waveforms that the data will be encoded on and then transmitted. But what we are seeing here are examples of analog signals. And then the definition for analog signal is saying that it is represented as continuous waveform. If you look at these waveforms, you can see that there are no breakages. They are continuous. That is the meaning, continuous waveform. And then it can be at an infinite number of points between some given minimum and maximum. So if you consider any point between these signals, so from here up to here, you realize that you can have infinite number of points in between because it is continuous. You cannot tell how many dots you would have to draw to form this line. They are infinite. So that is just the meaning. Given any 2 points in an analog signal, there are number of infinite points that forms the signal. So it says that it's how natural phenomenon like sound, light, temperature, voltage, and others exist in real world before we digitize them. We'll look at digital signals later. In data communication, analog signals are often the original source that gets converted to digital form for reliable transmission and processing. So naturally, our data exists in the analog format before we convert them to digital format for transmission. So our speech, that's the audio, voice, light, temperature, voltage, all these exist as analog forms before they are changed to digital forms for transmission. When it also comes to analog signals, you can see that the three signals here are all different. The common waveforms that we have in analog signals, we call the first one the sine wave, and this is what we call the pure sine wave. And then we also have a complex wave. The complex wave is a sum of multiple sine waves. So you can see that this is bigger, and then it comes to be smaller here, and then it goes back to be bigger. These are combination of multiple sine waves that have come together to give us a complex wave. And then we have what we call the non-periodic signal. The non-periodic signal is a signal that does not repeat itself at any point in time. So you can see here that it is not periodic as compared to the first sine wave. So these are some three forms of analog signals that we can have. The signal is represented as amplitude versus time, smooth curves that reflect how the signals evolve. So you can see that there is a reference point for our three signals. We have the y-axis here. The y-axis represents the amplitude of the signal. And then when we go into the characteristics of signals, we will understand what the amplitude of a signal is. So just know for now that the y-axis represents the amplitude of a signal, and then the x-axis represents the time in which the signal is traveling. Analog signals can take any value within their range. There are infinitely many possible amplitudes between 2 points. That is what I have explained earlier on, that if you pick this point and then this point, between here and then here, there are many points in between that are infinite. You can represent them in infinite number of ways. That's infinity, as many as you can represent them, because a line in itself, a continuous line in itself, has infinite number of points. So that is what it means. Any continuous signal can be decomposed into frequency using the Fourier transform, showing how much of each frequency is present. When we get to the frequency section, I think we can talk about this more. One primary shortcomings of analog data and analog signals is how difficult it is to separate noise from the original waveform. In our lesson 1, we briefly define what noise is. That noise is an unwanted signal that attaches itself to our desired signal and then deteriorates our desired signal. Noise in itself is analog. It's an analog signal. And then it's a signal that we don't want, but in a way it comes to attach itself to the desired signal that we are transmitting. And in analog signals, if you are transmitting an analog signal and then noise, which is analog, also comes to attach itself to your signal, it is very, very difficult to separate the noise out of your original waveform. So in analog systems, there's a big issue of noise. How can we separate noise from the original signal that we are transmitting? That is one main reason why digital systems were developed, because of the issue of noise. That is one. The most common examples of analog data is the human voice. Yes, so the normal speech that we do, they are all in analog forms. For example, when a person talks into a telephone, the receiver in the mouthpiece converts the airwaves of speech into continuous electrical voltages, which is analog. So this electrical voltage is what encodes your human voice. It changes your human voice into a form that the electrical voltage can carry. And then this is analog. And then it transmits it. And then it can store it. And then at a point in time, it samples it. We'll look at what sampling is. And then it quantizes it. So getting into digital signals, we'll look at what we mean by sampling and then what we mean by quantization. So your voice signal will be sampled and then quantized and then encoded and then transmitted. So this is an example of a typical human communication where your voice is analog. So if you pick up your phone and you speak, the voice you are sending to the phone is analog. But now we have digital phones. So your phone now will convert this voice onto a continuous electrical voltage, which is also analog. And this continuous electrical voltage will be sampled and then will be quantized, and then encoding will be done, and then your voice will be transmitted over the channel to your desired location. Now let's look at what digital signal is, and then after this I'll look at what we mean by sampling and quantization. A digital signal represents information using discrete, well-defined values rather than continuous varying waveform. In data communication, this enhances transmission, storage, processing, and making them more reliable and efficient and then resilient to noise. So if you look at these two examples, you will see a big difference between the signals we have been seeing and this one. See, it is saying that the signals are represented, the keyword here is discrete. Discrete means something that is not continuous. We represent them in discrete forms rather than continuous varying waveforms. So if you go up into the slide, you see that these analog signals are continuous varying waveforms. But in digital systems, we represent the signals as discrete waveforms. They break, you sample. So we are now coming to explain what we mean by sampling and quantization. So if this is our analog waveform, let's say this is our analog waveform, this is a continuous time varying signal. Here is our y-axis, which is amplitude. We have 0 volts here, and let's say that we have 5 volts here. We'll explain what amplitude is, so don't worry at this stage. And then the y-axis is the time through which the signal is traveling. Now, we are saying that this waveform that we have drawn is a continuous time varying signal. So it represents an analog signal, and that between this point and this point, you can represent this signal in an infinite number of ways, number of points, with an infinite number of points. So in between any point on an analog waveform, the values there are infinite. That is what we have explained so far. I wanted to give you a diagram here so that at least you will understand it better. Now, to sample an analog signal means that to take samples at regular intervals of the analog signal. So in digital systems, when they are converting analog signals to digital signals, they use regular intervals to take what we call samples of the analog signal. So these are the samples that I am taking. Instead of continuous lines, we are taking discrete values of the analog signal. And this is what we call sampling. So let's say that the digital system, at every 1 millisecond, it will take a sample of the analog signal that is entering it. So these are the samples that we have. Instead of a continuous signal, we have taken samples So the lines that we have drawn in between now forms our digital signals. Now we do not have continuous signals again. If we can clear the continuous line, and then we have something like this. Now this is our digital signal. See, in the first instance, instead of having continuous lines, now digital signals have discrete values. So you see that these are the samples that we took from our original analog signal. So this is what we call sampling. And then with quantization, now each sample will be matched to a specific amplitude level. So the digital system is measuring the analog signal that is coming in at a regular interval. And every interval, it takes a sample. So the first 1 millisecond, it took this sample. The next 1 millisecond, it took this sample. The next 1 millisecond, it took this sample. The next 1 millisecond, it took this sample. And then it goes on like that. So that is what happens with sampling. And then as it samples with quantization, after sampling, it matches what it has sampled with a specific amplitude level. So let's say that this is 1 volt, this is 1.1 volt, this is 2 volts, this is 3 volts, this is 4 volts, and then that is what happens. So that is how quantization and sampling is done. And that is the basics of converting analog signal into digital signals. The analog signals are sampled at an equal interval, and then after sampling, it is quantized. So now the system can know how to represent these sampled values, either as a 1 or as a 0. That is the short meaning of sampling and quantization. Just like the image I drew to represent to show the sampling example, the images you are seeing here, the signals you are seeing here are not continuous. So you can see here that this is representing a 1 here, and then here is a 0, and then here is a 1. So the signal is discrete. They are sampled at equal intervals of time so that it is not continuous. And then the next example here shows a more detailed or complex example of a discrete signal where systems often use multiple discrete levels in binary. So there are basically two levels, either a 0 or a 1, or an off or an on. So normally we represent off with a 0 and represent on with the 1. But there are other systems like the pulse amplitude modulation 4, which uses more levels. So for instance, at amplitude level 0, you can represent it with 0, 0, and then it is the off state. And then amplitude level 1, it can be a low state, and then amplitude level 2, it can be an on state, and then amplitude level 4, it can be a high state. So instead of having just 1 or 0 or on and off, it can have on and off an additional low or high. That is the meaning of the multiple discrete levels. When converting from analog, continuous amplitudes are mapped to the nearest discrete level. So when we took the samples from our analog signal, these were the samples that we took. So we can draw back our analog signal like something like this. So this would have been our original analog signal that we took the samples from. So these samples are mapped to a finite discrete level, and that process is what we call quantization. So with a system like this, for instance, the equal interval of time where the samples are taken depends on the system. I just use 1 millisecond as an example. It doesn't mean all the time. That is what happens. The time may vary. It can be 0.0001 microsecond or millisecond. It depends on the sampling technique that is used by the device. The main idea is to get as many samples as you can so that you can represent the signal as almost exactly as how it is. You realize that here, the more samples that you take, the more you will be able to represent the original analog signal. So that is just by the way of explaining what quantization is. You pick a sample and then you map it to the discrete level of the amplitude here. So this discrete level here can map to a 3-volt amplitude. That is what we call quantization. And by doing this, you are able to determine the state of a bit, whether the bit is a 0 or a 1. So the system can be calibrated such that, okay, if the sample falls below 2 volts, then it's an off state. And if it falls above 2 volt, it's an on state, so it's a 1. Or we can have multiple discrete levels where if the sample is below 1, it's a 0. If it's between 1.1 and 2, it's a low. If it's between 2.1 and let's say 4, it's a high. And if it's between 4.1 and 5, if it's between 2.1 to 4, it's an on. And then if it's between 4.1 to 5, it's a high. So these are ways where systems calibrate how the bits are generated, whether it's a 1 or it's a 0. The analog signal is sampled and quantized, and the process follows afterwards. So as I said earlier on, digital signals are read at specific intervals of time. We call that clock edges, and this ensures consistent interpretation of each level that you sample or you measure. Examples of digital signals are the text. Characters are encoded as binary using ASCII and Unicode. We've looked at this. And then images and then audio coding techniques that we looked at. They are all digital signals. Files and packet storage systems, the solid state drives, the random access memory, and then the central processing unit all store and manipulate data as binary into brackets charge levels and transistor states. For instance, the CPU, when a transistor is off, it is at a low charge level, and then a bit 0 is generated. When a transistor is on, it's at a high charge level, and then a bit 1 is generated. So always the signals are discrete but not continuous. It is either a 1 or a 0 or an off or an on. That is what we mean by digital signals. Why are digital signals used in communication? One is noise robustness. Because noise is analog, and then we try to convert an analog signal to a digital signal. With error detection and correction, it has made it more easily to remove noise from digital signals. So bear in mind that with digital signals, taking away noise is easier than doing that with analog signal. So small disturbances rarely flip a discrete level. So it is able to withstand noise better than the analog signal. Compression and efficiency. Digital data can be compressed. Now because of digital signals, we are able to compress data to save bandwidth and then storage. And then in terms of encrypting, authentication, and then checksum operation on binary data is much simpler than on analog signals. So these are the reasons why we will choose to have a digital communication system than an analog communication system. Nowadays, its interoperability is easy because there are standardized formats like ASCII, like Unicode, that all devices understand so that devices can communicate together. The protocols that are on the network are all standardized and every device can understand these same protocols. So these are the 4 reasons why digital signals or digital communication system is more preferred than an analog communication system. Noise, robustness, compression and efficiency, security and integrity, and then interoperability. So here we have the differences between signal and data. We've looked at what data is, and then we've looked at what signal is. Now let's try and see clearly the differences between them. If so far you've not recognized the difference, now this is the difference. A signal is a physical representation used to transmit information. And earlier on we said that it can be electrical, it can be light, optical, or it can be radio waves, which is electromagnetic. So these are the 3 main forms that signals take. Either optical, which is light, electromagnetic, which is radio, and then electrical, which is electric. But data, they are the raw facts or symbols that we need to transmit. And we transmit them by putting them or encoding them on a signal. So there are 2 different things. The data is not the signal, and the signal is not the data. There are 2 different things. The signal is what helps us to transmit the data. The signal is either electrical, optical, or electromagnetic. And the data that we are transmitting are the raw facts. And then signals can be either discrete or analog. But data is abstract. There can be numbers, text, images, audio. Signal is the carrier of the information or the data across the medium. And then the data is the actual content that we want to transmit. Signals can be measured using voltage levels, light pulses, or electromagnetic waves. These are the forms they take. But data are binary codes at the basic level. And then it exists to represent and transport data. And then the data needs the signal for it to be transported. Signals can be analog or digital, and then data can be in the form of text, images, and audio. And the signals must be decoded to retrieve the data. So if the signal gets to the receiving end, the device receiver has to remove the data from the signal. Data is meaningful once the receiver decodes it, and then we call that information. So from the definition of signal, you should know that the data is what we encode on the signal so that we can transmit them. These are the few differences that we have here. Now we'll move on to the characteristics of signals. Both analog and then digital signals have some characteristics. We want to look at those characteristics, and we'll be looking at 3 characteristics: the amplitude, the frequency, and then the phase of a signal. Now we've been talking about amplitude in this lesson, and I said we will explain it later. Amplitude refers to the strength of a signal in terms of how large its variation is over time. In waveforms, amplitude is the vertical distance from the center to the peak. So if you see this signal that is drawn here, this is the maximum amplitude and this is the lowest amplitude. So the definition says that it's the strength of a signal in terms of how large its variation is over time. So as the signal varies, the y-axis measures the amplitude. It's the vertical distance from the center line, which is the time. So from 0 upwards, we measure the amplitude. The amplitude directly affects the strength of the signal. So for example, if you have an audio signal, the higher the amplitude, the more louder it is. Or if you have any kind of signal, the higher the amplitude, the more stronger that signal is. Back to our original analog signal. To measure amplitude, we are saying that the amplitude is the distance from the center to the vertical. So this is the amplitude of this signal at this point. This is the amplitude of this signal at this point. And then this is the amplitude of this signal at this point. So at every point in time, the signal amplitude can be measured. But the peak amplitude is the maximum amplitude you can get for the signal. So this will be the peak amplitude. This is what amplitude is. Amplitude is the height of the signal at a given point. And according to what we have explained, then it means that the signal at this point is stronger than the signal at this point. And here is also stronger than the signal at this point. And here is also stronger than the signal at this point. And here may be the weakest point of the signal. We call this one the trough. And the trough represents the lowest part of the signal. And then we call the upper part the crest. So here is the crest, here is the crest, and these are the trough. So we have looked at the definition, and then we have looked at the impact, saying that the higher the amplitude, the more power or the greater the signal, the strength of the signal. Now we have also explained that amplitude is represented by the height of the signal. Types of amplitude. We have the peak amplitude, and then we have the root mean squared amplitude, and then we have the peak to peak amplitude. I will explain the peak to peak and then the peak amplitude with our diagram. So the peak amplitude is the distance from the center to the highest part of the signal here, from the center to this place. And then the peak to peak is from the highest point to the lowest point of the signal. That is peak to peak. But with root mean squared, statistical measurements representing the average strength or effective value of a varying signal. So as the signal varies along the path, from here you see that the amplitude is changing, it goes higher and then it drops. As the current varies, amplitude levels are taken from point to point, and these amplitude levels are squared, and after they are squared, the average of them is taken, and then after the average is taken, you square root it, and then that value is what we call the root mean squared. This is normally performed on alternating current where the signal varies a lot, so the amplitude changes a lot. So many amplitudes from that signal is collected, squared, the average is taken, and then you square root it to get the root mean squared, which will represent the equivalent direct current power, because direct current doesn't alternate. So these are the types of amplitude levels that we have. You should know we have peak amplitude, root mean square amplitude, and then the peak to peak amplitude. Now, how do we measure amplitude? Most commonly, we measure amplitude in volts for voltage waveforms, and most of the signal representations that you will see will be in voltages. And then we have other forms that we measure, like Pascal for pressure, and then in other fields also we can measure it in other intensities, but the common one that you find is in voltage waveforms, which we measure using volts, and the unit is V. So the unit depends on the physical quantity that you are measuring. The common one that you see is the volt. So the next characteristic of a signal is the frequency of a signal, and we define frequency of a signal as the number of complete waveform cycles that a signal completes in 1 second. So we can see the diagram here. This is a signal, and then from here, as you are seeing from the mouse, to this place is one complete cycle. From here to here is another complete cycle, and then from here to here is also another complete cycle, and then we move along, and then the time is from 0 to 1 second. So the time for the signal to make all this cycle, one complete cycle, is what we call frequency. So if you look at this signal made 4 complete cycles from here to here, which is 1, from here to here 2 cycles, from here to here 3 cycles, and then from here to here 4 cycles. So this signal that we are looking at made 4 cycles, complete cycles, within 1 second. And this becomes the frequency of the signal. So that is the meaning of frequency. The number of cycles a signal will make in 1 second is what we call the frequency of a signal. So you see here that we have written 4 Hz here. It means the frequency of this signal is 4 Hz because it was able to make 4 complete cycles in 1 second. So that is the easiest breakdown of frequency. In this diagram that I have drawn, can you estimate the frequency of this signal? Okay, by this time I guess you should have your answer. The answer is 3 Hz. Because the frequency of a signal is the complete cycle. This is the number of complete cycle in 1 second. This 1 complete cycle. This another complete cycle, making it 2. And then this is another complete cycle, making it 3. So this signal we have made 3 complete cycles in 1 second. So that is the frequency of the signal. Frequency has a relationship with the time that it takes to make the cycle. And the time that the signal uses to make 1 cycle, just one, not all the cycles in 1 second, from here up to here. So that's from here to here, from here to here. That is what we call the T, the period of the signal. And then the relationship between the frequency and the period is that the frequency is inversely proportional to the period. This is the unit of frequency. And this is how we represent it. With frequency, the higher the frequency, the more cycles per second. Looking at the formula, if you have a high frequency, it means this t will be very small, and then the number of cycles will increase. So the higher the frequency, the more cycles that a signal would undertake, and then the more faster its oscillation will be. As we see, the signal is moving up and down in cycles, so that is what we call the oscillation. And then the shorter the wavelength. We'll later look at the relationship between the frequency and then the wavelength of a signal. So it means that also the lower the frequency, the fewer the cycles, and then the slower its oscillation in terms of completing cycles. What impact does frequency have on communication? Frequency affects bandwidth. So the higher the frequency of signals, the more bandwidth that signal has. So it means that the higher the data rate of the signal. So if a signal has a higher frequency, it means it can carry more data. It has a bigger bandwidth. If it has a lower frequency, it means it has a smaller bandwidth, and then it can carry less data. That is the impact of frequency on communication. So all communication that requires higher bandwidth and faster data rates, the frequencies are higher. But those with lower data rates, the frequencies are lower. We've mentioned this, that the unit is hertz, represented by uppercase H and lowercase z. This is the standard unit for measuring frequency. So 1 hertz means that the signal underwent 1 cycle per second. Let's look at some of the common frequencies. Audio frequency, for instance, is between 20 hertz to 200 kilogram. So between 20 hertz and 20 kilohertz. So knowing this, you should be able to calculate the period for a 20 kilohertz frequency, because the formula is F is equal to 1 over T. So you can be able to calculate T. In radio communication, for instance, if you take Wi-Fi works in the following frequency bands: 2.4 gigahertz to 2.5 gigahertz. And then we also have one that works between 5.1 gigahertz to 5.8 gigahertz. And then the new Wi-Fi, the new standard, also works in between 6 gigahertz to 7.1 gigahertz. So these are the frequency ranges of Wi-Fi. So all devices that work in the Wi-Fi domain, some can work in this region, others can work in both regions, and others can work in all 3 regions. Or some can only have the 2.4 to 2.5, and others have, the new devices have both of them or the 3 of them. So this is the frequency range of Wi-Fi. Some mobile communication operate within the frequency of 600 megahertz to 900 megahertz. And others, like the 5G and 4G, operate here. And some also operate within 1 gigahertz to about 6 gigahertz. So These are typical frequency ranges for mobile communication networks, and this is for Wi-Fi. So every signal has a frequency range, and then the higher the frequency range, the higher the bandwidth. So Wi-Fi devices that operate at the 2.4 to 2.5 level has a lower data rate than the ones that operate at the 5.1 to 5.6, 5.8, sorry. And then the 6 gigahertz to 7.1 gigahertz is the fastest Wi-Fi we have so far, because they have higher frequencies, so the data rate will be higher. Why is frequency important? One, for channel allocation. Just like I mentioned, Wi-Fi has a range of frequencies they operate in, and then the mobile communication network also have a range of frequencies they operate in. So the frequencies have been allocated for every type of service. The FM stations and the radio stations also have their range that they operate in, between around 80 megahertz to 108 megahertz. So this is done so that we avoid interference, so that one service will not interfere with another service. They all have their frequencies they operate in. Then propagation. In terms of propagation, lower frequencies travel further and then penetrate better. Higher frequencies, as we said earlier on, support higher data rates, but they have shorter range. This is because of their wavelength. We'll get to know how we can calculate the wavelength. The wavelength is the length of a signal, one full cycle. That is the length of a signal in one full cycle. Lower frequencies have a bigger or a longer wavelength. They can travel far, but they have lower data rate. But higher frequencies have higher data rate, but they have shorter wavelength, so they can travel for short distances. In choosing frequency for your communication, it affects your antenna size, your hardware design, and then achievable throughput, because a higher frequency signal will have smaller antenna, and then the lower frequency signal will have a bigger antenna because of their wavelength. We'll look at wavelength later in this video, but let me give you a short image explanation of what wavelength is before we get there. Back to our analog sine wave. This is one full cycle of a signal. So measuring from here up to here, this is what we call the wave length of a signal. This is what we call the wavelength of a signal, the length of a wave in one full cycle. Lower frequencies have a longer wavelength than higher frequencies. So a higher frequency can have something like this, a shorter wavelength. So this is also the wavelength of this signal here. Another signal can also be here. This is the wavelength of this signal. This signal is higher than this one, and this one is higher than this one, because if we say that here is the time, 0 second to 1 second, the number of cycles that this one made is 1. So it is 1 hertz. So this signal is 1 hertz. If you continue this way, we can draw 2, 3, and let's say 4. So this one made 4 hertz, and then this one can also continue 1, 2, 3, 4, 5, 6, and this one becomes 6 hertz. So you see the time it takes to make one full complete cycle is short. This is what we call wavelength. So higher frequencies have shorter wavelength than lower frequencies. So that is the explanation of wavelength. When we get to the later section of this video, then we'll learn how to calculate the wavelength of a signal. Another characteristic of a signal that we want to look at is the phase. The phase of a signal describes the position of the waveform within its cycle at a given moment in time. In simple terms, the phase of a signal tells where the wave is at a given time. So for example, in the image that you see, you can see that at a given time here, the signal was at 0 degrees. We measure phase in degrees and in radians. We'll get to that. And then when it got here, the signal was at a 90-degree phase. And then here it was at 180. At the trough, it was at 270. And then here it was at 360. So within every point on the signal, we could have measured the phase of the signal. So the phase of the signal just describes the position of the signal at a given time. And we measure that in degrees or in radians. The image here is using degrees. Other images can also use radians. Example, at a peak or at a crossing or at a 0. So here is the 0, here is the peak, and then here is the crossing. Or at the trough, here is the trough. The relative reference is this line. And so we can measure the various phases of the signal at a given time. Phase is essential for understanding timing relationship between signals, interference, and modulation in communication system. Normally, we use phase to understand how different signals combine. For instance, if you speak into your phone or if you speak into a microphone, the signals travel at different positions. Some will collide and then some will come together. Those that will collide, if they are out of phase, it will cancel each other. And those that will come together, if they are in phase, then they will be constructive to each other. I will explain this one later in the next slide. So, as I've mentioned earlier on, the unit for the phase, measuring the phase of a signal is in degrees, and it's between 0 to 360 degrees. And then in radians, it's between 0 to 2 pi. We say relative phase between signals. We are saying that if signals are in phase, if the difference between two signals is 0 degrees difference, then the peaks will align and then the signal will have constructive addition. If two signals come together, if we say that the signal is in phase, that's what I want to draw. This is the first signal, and then this is also the second signal. You see that this signal has 0 degree difference. They look alike. They are not opposite to each other. So a signal like this, when they come together, that is what we call constructive addition. So this signal will now have a bigger amplitude. It will be bigger because they came together constructively. But if we have this signal and then another signal came in this way, this is signal 1 and this is signal 2. Then the resulting signal will either die out or it will be very small because these are out of phase with each other, so it will be destructive. It will destroy the signal. It will lower the amplitude of a signal, and then the signal will not be constructive. So that is what explains the timing of signals, and this affects interference. If they are in phase, there's no interference. If they are out of phase, there is interference, and then they will cancel out, or the signal will lose power. That is what it means. And then we use phase also to help carry data onto the signal. That is what we call modulation in communication systems. Controlling relative phase across antennas enables constructive combining. That is what I've shown in the description, or cancellation. We call the now steering. This slide is talking about the period, and then we have already talked about that, so we'll move forward. So these are practical examples here that we have to look at. We say higher frequencies have shorter periods and lower frequencies have longer periods. So for example, at a 50 Hz power signal, how do we calculate the time? The formula is T is equal to 1 over F. So here it's 1 over F. The F is this one, 50. That is why it is here. So the period for the signal, this power signal, to make one complete cycle, this is one complete cycle, is 0.02 second, or 20 millisecond. And then another example here, at 1 kilohertz, the time T is equal to the same 1 over F, and then the frequency here is 1 kilohertz, which is 1000. So 1 divided by 1000 is 1 millisecond. So at 1 kilohertz tone, that signal, it will take 1 millisecond to make one complete cycle. So this is how you calculate period from frequency. In the same way, you can calculate frequency from period. Now we explained wavelength earlier on in the slide above. Let's look at how we can calculate the wavelength of a signal. This is the relationship. The wavelength of a signal is velocity of the transmission medium divided by the frequency of the signal. So the relation to speed and frequency is that wavelength depends on the propagation speed v in the medium, and then the frequency of the signal. How do we measure wavelength? So in calculating wavelength we say is a relationship between the velocity and the frequency of a signal. And the velocity in air differs from the velocity in vacuum. So let's say for a sound, for instance, if you speak, your sound is in the air. Let's assume that you are speaking just through the air. If you want to calculate the wavelength of your sound, and let's assume that the sound that you made is 1 kilohertz of frequency. So your voice signal is 1 kilohertz. The speed of your signal in the air will be 343 meters per second. So now if you input them in the formula, we have velocity, which is 343 over the frequency, 1 kilohertz means 1000. And then now you have your answer here. And then the unit is meters. But in electromagnetic waves, we usually calculate our velocity as in vacuum or in free space. And that velocity is approximately 3 times 10 raised to the power 8 meters per second. So if you have a radio wave which has a frequency of 100 megahertz, so this is a typical FM station frequency. If this is the frequency of your signal, then what is your wavelength? Now, in free space or in vacuum, the velocity is this. So it will be 3 times 10 raised to the power 8 times 10 raised to the power 8. 10 raised to the power 8 here because the mega is 10 raised to the power 6 plus these two zeros is 10 raised to the power 8. Then we have 3 meters. So that is how we calculate the wavelength of a signal. We have already talked about the wavelength, that the wavelength is the distance between a 4 complete cycle of a signal. So with this 1 kilohertz sound, the 4 cycle of the wave, if we draw it, is this. The wavelength is 0.34 meters. So the distance is 0.343 meters. And then with this 100 megahertz radio frequency, the wavelength is much longer. It's 3 meters. So from here to here is 3 meters. So this is what we mean by the wavelength. 1 full cycle, the length of 1 full cycle of a signal is what we call the wavelength. So comparing these two results, the wavelength of this radio is longer than the wavelength of this radio, depending on the transmission medium they were traveling through. So that is the difference. Now we also have something we call the composite signal. The composite signal, these are waveforms that consist of multiple frequency components that have been added together. In the real world, for example, your speech or your video or your data, if you speak, your voice consists of a mixture of frequencies, both low and high. So your voice is not just one frequency. Your voice is a mixture of frequencies. So in the real world, most signals are composite in nature. As you speak, your voice is a mixture of low frequencies and then high frequencies. Now let's quickly look at bandwidth. We mentioned bandwidth earlier on, that higher frequencies have higher bandwidth and lower frequencies have lower bandwidth. What is bandwidth? The range of frequencies that is used to carry data is what we call bandwidth. And higher frequencies have bigger ranges that we can use to carry data more than lower frequencies. That is why we say higher frequencies have higher bandwidth than lower frequencies. So this is a very simple calculation here, that we are saying the bandwidth is the range of frequencies, the lowest to the highest, that we can use to carry data. So giving a typical example, bandwidth can be calculated as the highest frequency minus the lower frequency. Wider bandwidth generally supports higher data rate, just as how I have mentioned. And then to have a wider bandwidth, you should have a higher frequency. Example, voice telephony. Our telephone system has a bandwidth between 300 Hz to 3400 megahertz. So the bandwidth is the F high, which is 3400, minus the F low, which is 3000. So approximately the bandwidth of our normal telephony system is 3,100 hertz. Just 3,100 hertz is the frequency range with which the data that is being transmitted on the telephone line, your voice, will be carried. And then an FM broadcast audio base station, roughly, it has a bandwidth between 30 hertz to 15 kilohertz. If you do the subtraction, 15 kilohertz, which is 15,000 minus 30, is still approximately 15,000. So the bandwidth through which people sit in their FM station to speak and broadcast their voice to our radio set is approximately within 15 kilohertz. So in this lesson, we've looked at the part 1, how data is represented, and then in the part 2, we have looked at signals, and then we have looked at the types of signals that we have, 2 main types, analog and digital, and then we have looked at the characteristics of these signals, being amplitude, frequency, and phase. And through that, we have learned about the wavelength, the period, and then the bandwidth of a signal. So this brings us to the end of our lesson. Thank you for watching.